Welcome to Study Loop.
Okay, so we're doing chapter 18, problem 77. So this is going to use numerical integration, which we're just going to use some software for, but we're going to show you how to set up the integral to be what you need in the first place. So it says we want to estimate within 2% the fraction of molecules in air at a pressure of 1 atmosphere and T of 20 degrees Celsius that have a speed greater than, so we want to figure out all the speeds greater than Vmax times 1.5. With Vmax the most probable speed, not the maximum speed. So from the Maxwell-Boltzmann distribution, we know a few things. First of all, let's just write it out. Let's see, where did it go? Maxwell-Boltzmann distribution is given as f of v equaling 4 pi in m over 2 pi kbt to these 3 halves e squared e to the negative 1 half mv squared over kbt. Cool. So if we're looking to find the number of molecules that have certain speeds, if we want the number of molecules with speeds between v and v plus dv, this is given as f of v dv. And if we want the number of molecules between a range v1 and v2, this is the same as integrating f of v dv from v1 to v2. So first of all, from the Maxwell-Boltzmann distribution, we can find the maximum of this and figure out what v it's at. We do that by taking df dv, setting with 0, and then solve for that. And we see that vp is 2 kbt over m square rooted. So we now want to find all the number of molecules with speeds greater than 1.5 times that. So the equivalent integral expression for that will be our number that we want to find is given by the integral from 1.5 vp to infinity of f of v dv. So this is the integral we're wanting to find, but we're going to simplify this a little bit before we try and integrate it actually. So let's keep going. If there are in total, let's assume there are in total molecules, right? So in total is how many molecules there are. Then the fraction with speeds greater than 1.5 vp is just the number over the total. So if that's what we want to find the fraction of, we want to find this integral. Okay. So we also know that this is a probability distribution, so it must be normalized, right? So that means we know that 1 over n integral from 0 to infinity of f of v dv must be 1. That's what the normalization criterion tells us. So moving on now, we want our fraction. So this is our desired number over n, which is our fraction. And let's set this equaling to So we know this was 1.5 VP to infinity, but this is also, since these are probability distributions, 1 minus 1 over n of 0 to 1.5 dp. Excuse me. Okay, so this is the trick to make this integral easier for us to do here. So now that we have this, let's start doing some substitutions here. So I'm going to rewrite out the Maxwell-Boltzmann distribution. This is 4 pi n over 2 pi kbt, 3 halves, v squared exponential of n v squared over 2 kbt. Okay. So first, let's make x equaling v over vp, which is the same as v over square root of 2 kbt over m. If we do this substitution, then we have v squared equaling 2 kbt over mx squared, and our differential changes as dv 2 kbt over m dx. Awesome. So if we do this substitution, we now have our integral 1 over n 0 to 1.5 vp f of v dv. This now equals 1 over n 0 to 1.5 vp 4 pi n over 2 pi kbt 3 halves v squared e to the negative 1 half mv squared over kbt. Awesome. So that's what the integral is. And now we can rearrange this and know that if we're now switching to our x variable, 1.5 vp is just 1.5 in x. And let's start adding in. We know that the n's cancel out, so that's easy enough. And we're left with 2 pi kbt to the 3 halves, 2 kt over mx squared e to the minus x squared square root 2 kbt over m dx. This looks complicated, but hang with me just a little bit. So this now equals, we should see that we can simplify some stuff. So we're left with 4 up top. So we have m to the 3 halves over m to the 3 halves. So cancel, easy enough. We have kbt on the bottom to the 3 halves, and this kbt times this kbt over here gives us kbt to the 3 halves on top. Cancel out. So let's write the rest out now. So we have 4 pi times 1 over 2 pi to the 3 halves times 2, and these times 2 square root of 2. And this is what's left over, the integral of x squared e to the minus x squared dx. Cool. We can simplify this even more because this right here becomes 2 to the 3 halves. So these 2's are going to cancel, and now we're left with 4 over root pi. Integral from 0 to 1.5 of x squared e to the minus x squared dx. And now this is finally the point where we would numerically integrate this. We can also use computer software, and that's what we're going to do here. So let's compute this integral. We're going to compute it using Mathematica, and we should see that 4 over root pi integral from 0 to 1.5 of x squared e to the minus x squared dx. If we integrate this with our software, this becomes roughly 0.79. Cool. But remember, if we go back to our first page here, that's not the number we're trying to get, right? The number we're trying to get, sorry, that's up here, is 1 minus that. This is what we just found. So if we're trying to find our fraction, which was the number over the total number, that's 1 minus 0.79. And this comes out to being 0.21. Awesome. We finally got there.